Okay, today we're going to start talking about chapter 6, nonlinear regression models. The previous chapter concentrated on linear regression models, which was an amazing chapter. Now we'll move on to discussing nonlinear regression models. A typical form of a nonlinear regression models looks like this. First, on left hand side you have nonlinear regression models on both sides. G, Y, alpha is a nonlinear regression model equal to mu x beta. So this model is representing the dependent form, while this model is representing the independent function plus ut, while ut is the residual, which is IID n0 sigma square, which means independent and identically distributed zero mean with sigma square variance. The unknown parameter to be estimated are given by m plus k plus 2 vector, which is the structure dimension of the vector. Theta equals alpha, m plus k plus 2 vector theta, which is alpha, beta and sigma square. So to start with the example Zellner-Rivenker production function. Now this is the Zellner-Rivenker production function, which equals log of yt plus alpha yt equals beta naught plus beta 1 log of kt plus beta 2 log of lt plus ut, where the yt is the output, k is capital, L is labor, and this is the production function. So we can represent this production function with the typical form, which is g yt alpha. So instead of writing log of g yt alpha, instead of writing log of yt plus alpha yt, the left hand side form, we can simply write g yt alpha. Instead of writing the right hand side form, beta naught plus beta 1 log of kt plus beta 2 log of lt, we can write mu xt beta. If alpha equals 0, this can be intrinsically not nonlinear. Okay, so that is important. If alpha becomes 0 intrinsically, this can be intrinsically not nonlinear. Alright, so another example can be exponential regression models, as the example is yt equals beta naught exponential of beta 1 xt plus ut, where with the regular form we can represent it yt as a function of g, nonlinear function g yt alpha equals mu xt beta. The second part of the equation can be represented with the dependent variable function plus ut. Intrinsically not nonlinear means if alpha equals 0 in both these cases, these equations can be intrinsically not nonlinear, which means they cannot be transformed into a linear regression model. So basically what we understand is that whenever we are estimating a nonlinear regression model, we might need to transform those models to linear regression before proceeding. So this equation, if the second equation, the exponential regression equation, you see ut is outside of the coverage of beta naught exponential, but if yt equals beta naught exponential of beta 1 xt plus ut, which is ut on the other hand is outside the bracket beta naught exponential of ut, that becomes intrinsically not nonlinear, which cannot be transformed into a linear form. So let's coming back to the previous equation. So if log of yt equals log of beta naught plus beta 1 xt, so taking log on both sides of this exponential regression model, we have log of yt equals log of beta naught plus beta 1 xt plus ut. This is transformed into a linear form. Another example 6.3, alternative exponential regression model. Now y1t equals beta naught exponential of beta 1 xt plus ut. This cannot be, it's a intrinsically not nonlinear regression model. They cannot be transformed into a linear regression model. y2t on the other hand equals beta naught exponential beta 1 xt plus u2t, which is not intrinsically nonlinear, which cannot be transformed into a linear regression model. So the example when we will be solving it, a code will have t is equal to 50 observation, xt is linear, mu u1 u2 both are IID with 0 mean and sigma square variation, beta naught equals 1, beta 1 equals 0.005, sigma equals 0.5. With this information we will solve the problem with MATLAB R. Now moving on, as we have discussed 3 examples already, with some being intrinsically not nonlinear, with some being not intrinsically not nonlinear, Zellner-Rebenko production function that we discussed, exponential regression model and alternative exponential regression model. Now estimation, maximum likelihood estimation. ut is assumed to be normally distributed with density function ut equals 1 by root over twice by sigma square exponential of minus u1 square by 2 sigma square, or transformation of variable. Using transformation of variable technique we need to transform ut to yt, where the density function of yt equals fut ddyt for of ut, and taking derivatives with respect to it, or ddyt of ut equals the nonlinear function dgyt alpha ddyt of dgyt alpha, the nonlinear function of the first portion. So the conditional probability of the distribution of yt becomes fyt conditional on x for all parameter theta equals 1 by root over twice by sigma square exponential of minus gyt alpha, which is the nonlinear function for the dependent variable, minus mu xt beta, which is the nonlinear function of the independent variable, squared divided by 2 sigma square. And in absolute form we have ddyt of gyt alpha, the nonlinear function of the dependent variable, but the unknown parameters are theta, alpha, beta, sigma square. The log likelihood function for t 1 to t observations are log of LT theta 1 by t summation of log of f y function of yt, the conditional probability distribution of yt, which is 1 by t, or mean, taking mean of summation of log of fyt conditional upon xt for all theta parameters, equals mean of log of LT theta, which equals minus log of half log twice by mean log twice by minus mean log sigma square minus 1 by 2 sigma square t, where we just the numerator of was gyt alpha, the nonlinear function of the dependent variable, minus mu xt beta, nonlinear function of the independent variable squared, plus mean of log the second term d dyt of gyt alpha, So basically nothing but representing the previous conditional probability distribution function in here. Very simple. Maximizing with respect to theta, we have the gradient vector where the vector parameters are mean of d alpha of log LT, mean of dd beta of log LT, mean of dd sigma square of log LT. So all will be 0 in the first order condition. So the first concentrating out dd alpha of log LT equals minus, well, we have to just look into the equation and taking calculus against alpha, differentiating for alpha, we have minus 1 by sigma square multiplied to minus 1 by sigma square g y t alpha minus ut x t beta, this portion multiplied to d g y t alpha divided with dy t, because in all these cases we have alpha. Okay, plus okay, dd alpha of log of dy t, so dd alpha of log of dy t for g y t alpha. Okay, so this is simply the second form of the equation, where the first form of the equation is when we take concentrate out this portion, then dd beta of log LT, because in the second form we don't have beta. Beta is coming from the independent probability distribution function, density function, or the independent nonlinear function. So here we don't have any independent nonlinear function element. Here we have both of the elements, independent and dependent nonlinear function elements. So dd beta of log LT is 1 by sigma square, so we are remaining with 1 by sigma square, and simply just like earlier, the function differences, the functions, nonlinear functions differences, multiplied to dd beta of xt beta, because this has both the dependent and independent nonlinear functions in them. Then comes sigma square, dd sigma square of log LT, because we are talking about sigma square, all the sigma square element will come. So here it turns 0. Then we have minus half sigma square plus half, because we are differentiating against sigma square, sigma to the power 4, where multiplied to this portion, the difference portion. So with this information against 0, we have gradients. The Hessian becomes well, mean in all cases, then d square log LT by d sigma square, d square log LT, d sigma square is multiplied, well, here is actually dd alpha of log LT multiplied to dd alpha of log LT, dd alpha of log LT multiplied to dd alpha or dd beta of log LT, so d square log LT, this portion dd alpha of log LT multiplied to dd sigma of log LT, by rows down is just dd alpha of log LT being multiplied to everyone. Then well, here also the same, dd alpha of log LT multiplied to dd beta and dd alpha of log LT multiplied to dd sigma square. So cross this out, then in diagonally down the row we have dd beta of log LT, multiplied to dd beta of log LT. Now this is the dd beta of log LT rho. So dd alpha of log LT multiplied to dd beta of log LT becomes the same. This equals the same. dd alpha of log LT multiplied to dd beta of log LT multiplied to dd beta of log LT. dd beta of log LT multiplied to dd sigma square of log LT. You see, these two ends are same. So because we have dd sigma square dd beta multiplied to dd sigma square of log LT, now this one starts with dd sigma square log LT multiplied to everyone, dd sigma square of log LT multiplied to dd alpha of log LT. These two become same. dd sigma square of log LT multiplied to dd beta of log LT. You see, they become the same. And diagonally we have dd sigma square log LT multiplied to dd sigma square of log LT. So in all these cases, dd alpha of log LT multiplied to dd alpha, which is the d square log LT divided by d alpha transpose. So basically in matrix, in structural bar, we don't do dd alpha square, rather we do dd alpha multiplied to d alpha transpose. So we are already familiar with this form. You see, previously this is the form we had. We derived this form. The only difference is now instead of d alpha we have d alpha transpose as well, minus 1 by sigma square. This is new, d alpha for the nonlinear portion, then d alpha transpose, d alpha for the nonlinear independent dependent function, then d alpha transpose for nonlinear independent function. So for one for alpha and one for alpha transpose, minus, then plus d square again d alpha transpose log of. This is the second form, second part here. So what we are doing, just focus in here. The first portion is exactly the same, minus in the second part we have starting with 1 by sigma square, then we represent dd alpha of the function, nonlinear function, then dd alpha transpose of the nonlinear function, plus now this portion is multiplied with the transpose, d alpha transpose, so d square divided by d alpha transpose multiplied to the remaining stuff. So this is how this will look. Now d beta square, what will change in d beta square? In d beta square we will be remaining with the equation as it is. Only difference is it will start with a minus, and the last part will change. The last part will have dd alpha with the nonlinear function g yt alpha, then dd beta transpose with dut. So this becomes dd beta transpose. But no, we are not talking about d beta squared, I'm sorry, we are talking about d alpha d beta. In case of d alpha d beta, how will we represent? So obviously we'll have d alpha and d beta. So d beta transpose, we're talking about d beta transpose, and this portion we're talking about d beta transpose with mu xt beta. This remains the same. We'll just add dd alpha of g yt alpha, this function. This portion is only added and starts with a minus. Now we're going to talk about the beta square. Now when we are talking about the beta square, you see, just like d log LT d beta, everything remains same, nothing changes up to that point. And well, in that equation we had d mu xt xt divided by d beta, or d beta of d mu xt. We'll also have obviously the beta transpose, because we are talking about d beta square. So beta transpose is the new form that will be multiplied minus just like the first equation, we'll have another form: 1 minus sigma square dt beta of xt and dt beta. So well, basically because we have two betas now, beta and d beta transpose, so d square dt beta of d square mu xt beta dt beta of transpose of mu xt beta. So this is the new part that is added to the equation. What will happen when we have sigma whole square? Sigma square is 1 by 2 sigma to the power 4 minus 1 by 2 sigma to the power 4. Yeah, this is as it is. Here our equation changes because we are comparing this with dd sigma square of log LT. We are just simply comparing this with this equation, and in the new equation, as we can see, in the new equation, in the second part, instead of writing plus 1 by 2 sigma square sigma to the power 4, we are simply writing minus 1 by sigma to the power 6. Rest of the function, the function difference remains same. There is no change in the function difference because variance is the residual variance. So basically this will not change because dependent minus independent, taking everything on the left hand side, we are remaining with the variance of the residual. Then d alpha square, well, nothing changes except this part compared to when we were only talking about dd alpha of log LT theta, dd beta of log LT theta. The sigma square becomes sigma to the power 4 in both cases. That's the only change. The function difference is there in both of the equations, and this portion is also available in both of the equations. Now the second part of dd alpha of log LT is not here. Okay, so that is another difference. So major difference when taking square is that this additional portion in both of the equations that arrive, this additional portion when we're talking about d alpha transpose, and this additional portion when we're talking about d beta transpose. D alpha transpose had even further additional information. On the other hand, d beta transpose didn't have that indeed following the main equation. So the parameter updating scheme of Newton-Raphson is theta k equals theta k minus 1. So given theta k minus 1, we are calculating theta k minus gradient divided by Hessian of the previous parameter estimation. So first we have previous parameter estimations and we have the gradient and Hessian of that estimation. We deduct that and we get the updating scheme, new parameter estimation, and this will iterate until convergence. In the context of a nonlinear regression model, the Newton-Raphson algorithm is simplified by concentrating sigma square from the log likelihood function. So we need to take a concentrated sigma square from the log likelihood function by expressing sigma square with sigma hat square as a sigma hat square as a function of beta hat and alpha hat. Both are all, which means all are estimated parameters from theta k minus 1. This is achieved by solving the first order condition for which sigma hat square has the solution. So solving first order condition, we get alpha hat and beta hat. Estimating those parameters, we had sigma hat square, which is mean summation of simply the difference between the dependent and independent nonlinear function whole square. That's all, very simple. Maximization of log likelihood function is performed by redefining the unknown parameter vector theta alpha beta with iterations computed as we just said, theta k equals theta k minus 1 minus gradient of and Hessian of the earlier parameters. So gradient, this is same as discussed before, dd alpha, well, for dd alpha and dd beta, and Hessian starts from dd alpha, okay, multiplied to itself, then this second column starts with dd beta multiplied to dd alpha, this one multiplied to d beta delta alpha transpose, this is multiplied to d beta transpose. While both of these looks same, the parameter estimations and everything is same as well. So sigma square is now replaced by equation 1. So replacing sigma square by equation 1, we have this coding algorithm. So replace my negative Hessian with information matrix I theta. So we have gradient divided by Hessian. Instead of that, instead of negative Hessian, we can write I theta information matrix theta, and that equation becomes theta k equals theta k minus 1 plus gradient divided by information matrix. We know that information matrix equals outer product gradient OPG. The information matrix is given by its expected value of, well, this is nothing but the this is nothing but a Hessian, whatever inside the Hessian is there, except for we have a negative sign. So information matrix is nothing but negative expected value of the Hessian. So example 6.4, estimation of a nonlinear production function. So let's consider the Zellner-Ravenker production function. The probability density function of residual ut is the 1 by root over twice by sigma square exponential of minus ut square divided by 2 sigma square. Using this with the equation that we have just discussed, this one becomes ddyt of ut. So we are doing transformation of variable technique. So transformation of variable technique gives us 1 by yt plus alpha. So the conditional density function for yt is now the conditional density function of, so dyt is 1 by yt plus alpha, because as we're just gonna go back and have a look into Zellner-Ravenker production function. Okay, just bear with me a moment. See, 1 by yt plus alpha. So here, because of log, we have 1 by yt, and this one becomes simply alpha because yt becomes 1. So that was the Zellner-Ravenker production function, and there you go. Yt square ut square minus 2 sigma square. This is the conditional probability density function and this is the representation when we are taking difference on the log of the dependent variable, nonlinear dependent variable function. The conditional density function for yt is, well, function of yt conditional upon k for information matrix I and all parameters theta. We have 1 by root over twice by sigma square exponential of minus, well, this is the whole equation, log of yt plus alpha yt minus beta naught plus beta 1 log of L log of kt minus beta 2 log of LT whole square multiplied to the representation that we have just received, dy of ut. So this is the whole equation basically. This is left hand side, this was right hand side. We take everything on the left hand side, we are left with the residual ut. This is the representation of the residual, so whole square ut square divided by 2 sigma square, exactly same thing. And this is simply f ut. This is the transformation of variable f function of ut, conditional probability density function f ut multiplied to derivative of ut. So that gives you the transformation of variable technique. That's all, nothing else. So now with that, as ut has been transformed to yt, step 1 of the log likelihood function for t equals 1 up to t is log of LT minus half log plus pi minus half log sigma square minus 1 by t plus 1 by t this part, log of this part minus 1 by 2 sigma square t, 2 sigma square t because it was squared, summation of 2 sigma square t 2 sigma 1 by t 2 sigma square, simply that 2 sigma square t multiplied to the summation of the entire term. That's all, very simple. The log likelihood function is this. Step 2 is maximizing with respect to theta parameter, which is alpha, beta naught, beta 1, beta 2, sigma square, and concentrating log likelihood with respect to sigma hat square given by the variance of residuals. So what was sigma hat square? Sigma hat square was 1 by t summation of the g yt minus mu xt whole square. So here 1 by t summation of g yt, this is what g yt represents, minus mu xt, this is what mu xt represents, whole square. Same thing, very simple. So that is example 6.4 when we concentrate out log likelihood with respect to sigma square hat, and that is essential to concentrate out sigma square hat because Newton-Raphson algorithm will be simplified given the sigma square hat, that we will check. Example 6.5, estimation of a nonlinear exponential model. So first, the conditional probability density function of the residual f yt is equal to 1 by root over test by sigma square exponential of minus ut square by 2 sigma square. And then because we have to go again with the variable of transformation technique, we have function of yt conditional density function of yt equals 1 by root over 2 s by sigma square exponential of ut is yt minus beta naught exponential of beta 1 xt whole square by 2 sigma square. This is coming from the exponential distribution function, which equals to the residual ut and the minus vanishes in the transformation, it becomes positive. So the log likelihood function, so the log likelihood obviously it will be because minus minus becomes plus, that's why. Still, I'll just check quickly in 1 second. Yeah, this is G, right? So because let's go back and let's go up. I'll show you. See, minus with the transformation technique, the minus vanishes. The minus here minus this minus plus gives us the positive function. The log likelihood for t equals 1 to t becomes simply the log likelihood function of this equation. That's all. 1 by log twice 1 by log sigma square 1 by 2 sigma square t, and this one very simple. Maximizing with respect to theta, and theta has beta naught, beta 1 and sigma square. We have dd beta naught, dd beta 1, dd sigma square. So 1 by sigma square t, 1 by sigma square t, everything remains the same here. By t minus beta naught beta 1 xt multiplied to exponential of beta 1 xt, beta minus beta naught beta 1 xt multiplied to, because we're talking about beta naught, this is now here we're talking about beta 1, so beta 1 is within beta naught exponential of beta 1 xt. So this is the changing part, this is the changing part, and sigma square, we have 1 by 2 sigma square minus plus 1 by 2 sigma to the power 4 t, and this whole part. That's all. So this is only the changing part that we need to remember. So estimate maximum likelihood estimation parameters, concentrating the variance or concentrating the log likelihood function out. We have sigma hat square equals that equation part. Now using MLE estimates based on concentrated log likelihood function, if these are the estimation parameters, initial estimation, to find Hessian and covariance matrix, we need to use Hessian for covariance matrix, which is minus mean negative Hessian of beta, and standard errors are found by taking square root of diagonal terms of the covariance matrix. Square root of diagonal terms of the covariance matrix gives us the standard errors. The residual at time t is yt minus beta naught. Well, just taking the equation on the left hand side and right hand side, we have the residual. So we have covariance, which is mean, negative mean, inverse Hessian of beta estimated parameter, beta 1 or beta. Diagonal, we take square root of the diagonal elements of covariance matrix, we are remaining with standard error, and residual sum of square is simply well, take estimating ut or the residual variance, residual sum of squared is, we already estimated residual, this time we just sum all residuals up, we have residual sum of squares. Finally the residual variance sigma square is 1 by t. This is the equation part. Well, is there any change in the equation part? No, it remains same. So with the residual sum of square, we use sigma hat square to update this information. With standard errors, sigma square is equal to root over 2 sigma hat to the power 4 by t. Okay, standard error is root over 2 sigma hat to the power 4 by t. Next is Gauss-Newton algorithm. So up until now we have talked about Zellner-Rabin curve production function, we have talked about exponential distribution function and how we can solve them. We have also talked about scoring method and updating scheme of the parameters using Gauss-Newton algorithm. The Newton-Raphson algorithm, and scoring was simply replacing the inverse Hessian with information matrix I theta. That's all. Now we are gonna move on to talk about Gauss-Newton algorithm. For the special case of nonlinear regression model, GYT theta equals YT, the scoring algorithm can be simplified further so that the parameter updating can be achieved by means of least square regression. So OLS uses Gauss-Newton uses OLS regressions, and so the scoring algorithm we are trying to simplify it further. The form of this scoring algorithm is known as the Gauss-Newton algorithm, which uses OLS indeed. So let's consider this regression model where we are not talking about the non-linear function of yt, rather we are simply expressing the equation with yt equals the non-linear dependent variable mu xt beta plus ut. This is a special case where the dependent variable is not non-linear. Ut is independent and identically distributed with zero mean and sigma square variance, with unknown parameters theta equals beta and sigma square. The conditional distribution of the dependent variable yt is, well, as you are already aware of the conditional distribution function, yt conditional on xt for all parameters equals 1 by root over twice by sigma square exponential of, well, the residual yt minus mu xt beta whole square divided by 2 sigma square negative 2 sigma square. And the log likelihood function at time t is taking log here 1 by 2 log twice by 1 by half log sigma square minus 1 by 2 sigma square yt mu xt beta whole square. Very simple. With the first derivative is 1 by sigma square dd beta of mu xt beta. We're taking the equation out. On the right hand side, the first equation is well, the first derivative is dd beta of sigma square. That's all, because we are only concerned with beta now. We don't have alpha here, so we are only concerned with beta. Or we can represent, well, this is basically known to us as ut. We can represent this with zt, which is dd beta of d mu xt beta, or simply dd beta of the non-linear dependent independent variable. Very simple. So we have the first derivative to be 1 by sigma square zt ut. Gradient vector with respect to beta is 1 by t g, well, the gradient vector of beta, which is 1 by sigma square t zt ut. So simply 1 by t is added here. Gradient first derivative is 1 by sigma square zt ut. Gradient vector, the whole with respect to beta, is simply t is added. And so the information matrix is gradient multiplied to gradient 1 by t, gradient multiplied to gradient transpose, which is 1 by t zt ut. Well, as just replace gt with the values that we have derived. Or this can be represented with, well, 1 by sigma square 4. What do we have here? Yeah, sigma square 4 t, because this was, well, yeah, expected value of ut square, because ut transpose is same thing, zt transpose t equals 1 to t. Or Well, furthermore, this is basically coming from residual variance is sigma square cuts off. But expected value of t is always 0. Nothing is there. Expected value of t is not 0. Nothing is there. That's why nothing came off. There is no, calculation here. Very simple. And expected value of t means nothing. Expected value of sigma square is sigma square. That's all. So 1 by sigma square t expected zt transpose, where ut is IID with 0 mean and sigma square variance, and expected value of ut square is equal to sigma square. So this is the information matrix. 1 by sigma square t is zt transpose, and what was zt? Very quickly is with the first derivative of the log likelihood function. The first derivative of the log likelihood function, we have 3 elements. 1 by sigma square is the first element that we mentioned. The second element is the beta of the mu xt beta, which is the nonlinear function of the independent variable, dd beta of that, multiplied to the regular equation is the residual, which equals to the residual. So now we can implement Gauss-Newton because we have ZTUT. Now you can implement Gauss-Newton by approximating the expression for information matrix beta. So we already have the information matrix of beta that we have just derived. So, and evaluating this expression and the gradient, the total gradient GTB at beta k minus 1, which is the previous estimation of the parameter when we are referring to updating Newton-Raphson scheme. The iteration proceed according to the current estimation of beta parameter equals the previous estimation and the previous estimation of the gradient. So bk1 inverse in the previous estimation again, information matrix multiplied to the gradient. So basically plus, it was Hessian, it was negative when it was Hessian, it is positive when it is information matrix, gradient divided by the information matrix. Or we can replace the gradient and information matrix with ZTs and UTs that we derived earlier, and information matrix with ZTUT was 1 by sigma square t expected value of ZT transpose. For gradient 1 by sigma square t ZTUT. So we have ZTUT here. First think about the gradient, where it was ZTUT divided by sigma square t divided by ZT transpose divided by sigma square t, or just take this in the upper portion. We have sigma square t going up, sigma square t, and ZT we are remaining with ZTUT divided by ZT transpose. Very simple. So, and then bk minus 1 is del ZT is this portion. So very simple. Sigma square t goes up, ZT transpose goes down. This is a mistake in writing. The Gauss-Newton algorithm now requires evaluation of residual UT and ZT at previous beta estimation at beta k minus 1, followed by a simple linear regression of UT on ZT is obtained. So now we need to find ut and zt to obtain this delta hat. So parameter estimates from beta k minus 1 iteration plus parameter estimates from beta k iteration gives you the updated parameter vector at beta k. So parameter estimates of beta k minus 1 and parameter estimates of beta k both are required. See, so interestingly now we need ut on zt. So what are the steps to go through? One more time. First we need to find the gradient with respect to first we need to log likelihood, we need to do first derivative, we need to do the gradient vector with respect to beta and the information matrix with respect to beta. So this is the fourth step. Then after that we need to find ut and zt, probably with OLS with beta, to find delta hat, and then we use delta hat to update beta k minus 1. Once Gauss-Newton scheme converges, the estimates of beta hat are maximum likelihood estimated. The maximum likelihood estimation of sigma hat square equals 1 by t summation of yt minus mu xt beta whole square. So an example, nonlinear exponential model, revisiting nonlinear exponential model. So we will need these up until Gauss-Newton scheme converges and we get this sigma hat square. So our objective in all cases, Newton-Raphson and Gauss-Newton, is to get sigma hat square or sigma square hat. That is necessary for us to find covariance and everything. Nonlinear exponential model is this, as we know. Estimating this model using Gauss-Newton steps. Step 1, compute derivatives of mu, the nonlinear dependent independent function, nonlinear independent variable function. So with the derivatives with respect to beta naught and beta 1. So z1t and z2t du of xb, beta naught du of xb, beta 1. At beta naught we have exponential of beta 1 xt because beta naught is 1. At beta 1 we have exponential of beta 1 xt, and with beta naught there is another x added. That's all. These two, this is the first step, the maximum likelihood. So we need to compute z1t and z2t, then evaluate ut, z1t and z2t at starting values of beta. We need to estimate ut, z1t and z2t. Now we need to regress ut on z1t and z2t to obtain delta hat beta naught and delta hat beta 1. And we need to update the parameter estimates at iteration k equals 1. Now we need to update the parameter estimates with beta naught beta 1 k equals beta naught beta 1 k minus 1, the previous parameter estimates plus the estimated parameters. So we already had previous estimation and we estimated beta naught beta 1, we add them together and we have the updated parameter estimates at iteration k. Then comes step 5, which is the iteration will continue until convergence is achieved. So at the default tolerance level, this iteration will continue up until beta naught and beta 1 is less for all values up until beta naught and beta 1 reaches the tolerance level, as it is less than the tolerance level. So estimating a nonlinear consumption function in example. Okay, so the consumption function beta naught, so we just did a nonlinear exponential model function, a nonlinear consumption function beta naught beta 1 yt beta 2 plus ut is id and 0 sigma square. Serial consumption, yt is real dispensable income, disposable income or dispensable income, same thing. ut is id and 0 sigma square, that is independent of yt and theta. and in theta we have obviously beta naught, beta 1, beta 2, sigma square, blah blah blah, y beta 2, because yeah, obviously yt beta 2 are unknown. Estimate the model using Gauss-Newton, not Newton-Raphson. See, Gauss-Newton algorithm. So step 1, compute derivatives of the yt. Compute derivatives of yt, beta naught plus beta 1, which is simply beta naught plus beta 1 yt beta, with respect to beta naught, beta 1 and beta 2. So z1, z2 and z3. z1 is with respect to beta naught is 1, then with respect to beta 1, yt beta with respect to beta 1, we have what, yt, we have what, yt beta 2, indeed. Okay, and this is beta 2, yt beta 2, and z3 with respect to beta 2, we have beta 1 yt beta 2 log of yt, bigger term. Beta 1 yt beta 2 goes out and the log of yt. Indeed, we are taking log here. So we evaluated z1, z2 and z3. Now we need to evaluate ut, z1t, z2t and z3 at the starting values at beta. Then we need to regress ut on with OLS on z1, z2 and z3 to get delta hats, and then we need to simply add these delta hats to previously estimated parameters beta naught, beta 1, beta 2 to get the updated parameter. This beta naught, this whole thing will continue in a loop. Well, basically this equation will continue to update with the updated beta naught, beta 1, beta 2 until beta naught, beta 1, beta 2 convergence to the default tolerance. There is a specific example in the book from March 1960 to December 2009 with this data. The nonlinear consumption function of US is calculated with iteration, where we first beta naught and obtained from a linear model. Beta naught and beta 1 is obtained from a linear model. Beta 2 is 1, and the obtained vectors for beta naught is this. So with all these up to that, delta hat is estimated from zt and updated parameter is this. Final estimate after k equals 5 iterations is beta 5, which is achieved after 5 iterations. Estimated residual for time t using parameter estimates at final iteration is computed as ut. So ut is computed yielding the residual variance sigma square. So at the end ut is computed, sigma square is computed from ut, because sigma square is simply summation of ut square divided by t, or mean of summation of ut square, and then with this information matrix is obtained, which is zt transpose divided by sigma square t, or simply the information expected negative expected Hessian is the information matrix. From here the covariance matrix is simply divided, the whole thing divided by t. Information matrix, well, 1 by t inverse of information matrix, that's all. You multiply this with 1 by t and take the inverse of this function, that's all. You have covariance. Standard error is root over covariance is standard error, beta naught, c, beta 1, beta 2. So these are the standard errors located. Very simple. So now relationship to nonlinear least square. A standard procedure used to estimate nonlinear regression model is known as nonlinear least squares. Considering yt equals mu, considering yt equals mu xt beta or mu xt plus ut, where for simplicity beta is a scalar By expanding mu xt beta, or simply the nonlinear function of xt, as a Taylor series expansion around beta k minus 1, we're talking about nonlinear least squares now. Beta equals xt beta equals mu xt beta k minus 1 plus dd beta prime, dd beta transpose of u beta minus beta k minus 1, plus that will continue. So from this equation we have mu t can be written, mu xt beta can be written as yt minus mu xt beta k minus 1, yt minus mu xt k minus 1 equals dd beta transpose of u beta minus beta k minus 1 plus vt. Vt contains ut and higher order terms from Taylor series. The kth iteration of the nonlinear estimation procedure involves regressing this part on the derivatives of du d beta to generate parameter estimated. So on the derivatives of dd beta of u, this one regressed on dd beta of u to generate parameter estimates delta hat equals beta k minus beta k minus 1. The updated value of the parameter estimate is then computed so that we simply get beta k equals beta k minus 1 beta k equals beta k minus 1 plus delta hat, which is used to compute back yt minus mu xt and dd beta of mu xt beta. The iteration proceeds until convergence. Basically this is an updating scheme. An alternative way of expressing the linearized regression equation in yt mu xt plus ut is to define ut is equal to yt minus mu xt beta k minus 1 and zt dd beta of mu xt beta k minus 1, and this is the delta form. So ut is zt, and write the equation as ut equals zt transpose beta k minus 1 plus vt, an important equation. At least square regression of ut on zt yields a least square regression of ut on zt yields delta hat, as we already know, which is the equivalent updated Gauss-Newton estimated. So this is establishing the relationship of zt with ut with a nonlinear regression, nonlinear least square regressions. Relationship to values. For classes of models in gyt equals mu xt plus u, the nonlinear functions, the general from nonlinear functions, gyt is linear in yt, and mean function mu xt is linear also. Here the Gauss-Newton algorithm converges in one step. Consider the linear regression model in which mu xt equals beta xt transpose, and the expression for mu t and zt are respectively, just the residual yt minus beta xt transpose in case if it is linear, and zt is dd beta of mu xt, dd beta of mu, which is xt. Evaluating this expression at beta k minus 1 and substituting into the Gauss-Newton algorithm in the equation after rearranging delta hat, which is beta k minus beta k minus 1, which equals zt by zt transpose, we have beta k equals beta k minus 1 plus xt, summation of xt, then instead of ut we have the ut's equation divided by xt transpose, or xt yt minus, just two simple calculation, xt transpose, then these cuts off, you have beta k minus 1 left, goes out, we have xt yt divided by xtst transpose. So wow, from zt's we have xt's. So if our model class is linear, then we have linear regression model. You see, this is the skin converges to OLS. This is simple OLS in just one step. So that justifies the iteration process. In case of linear, it will automatically by default convert to OLS. If it is non-linear, then we can go on using updating scheme, and basically it is equivalent to OLS estimator. That is the point of this discussion. Okay, we have studied up until now. We can proceed on solving some of the problems. So the first problem is simulating exponential models. The problem is NLS simulate whether we'll start with exponential model. The exponential model is given, y1t is given by, you see, these cannot be transformed to a linear model, as if you can recall, because this is intrinsically not non-linear. But the second model is intrinsically linear, beta naught exponential of beta 1 xt ut. But the exogenous variable is a time trend, and the disturbance term ut is IID n0 sigma square. So simulate the exponential model for a sample size of t equals 50 with parameters beta naught equals 1, beta 1 equals 0.05, and beta 2 equals sigma equals 0.5. What I'm trying to do right now is trying to find out the problem. Yeah, so just bear with me a second. So as you can recall, this is the problem that we were just discussing. So beta naught, beta 1 xt ut, you see, this is the problem. And even I mentioned earlier, this information was given, so that's what we are doing now. Plot the level of the series y1t, y2t and the logarithm of the series log y1t, y2t. Discuss the time series property of the time series. Repeat with beta naught 50, beta 1.5, sigma 0.5. Reduce the signal to noise ratio by choosing the parameters beta naught 1, beta 1 0.05, sigma 5 instead of 0.5. Demonstrate that the natural logarithm transformation is no longer an appropriate method of explaining the trend for the series y to t. Okay, simulate. So this is the MATLAB equation. We'll see if we have any local functions. No, this is basically a graphical representation problem. So random stream set global stream, well, all true, all equals true is, list equals is rm, then graphics off, then set.seed 1 2 3 4, this is 1, kind is Mersana twister. So t equals 5, this is the package that we need to load. So and the simulation is presented with a function, and the simulate for r, yeah, t equals 50, beta naught 1, beta 1, given information sigma 0.5, u equals u is now simulating. We are gonna simulate the residual. Based on residual, we are gonna simulate the rest y1 and y2. That's very simple. So residual is sigma multiplied to random number of t rows for first column, sigma r norm t, x is 1 to t transpose by 1, x is 1 to t, it will automatically do it by 1 by default. So beta naught exponential of beta 1 multiplied to x plus u, because it's not a matrix multiplication, is a vector multiplication, so percentage signs will not come. So we're just going to represent both of the equations, and that's all. That's all for the first problem. It generates y1 and y2. And so next comes plotting regular plotting. You see, we're just plotting with red color. Type is linear. This is the main title. Expression of xt is presented in x lab. Expression of yt is presented in y lab. Okay, simple lines instead of like subplot, doing subplots here. So just graphical presentation. That's all for our basically. So there are just two portions in the graphical representation. First portion, then the second portion. We are joining two plots, log yt, legend goes to top right, expression of y1, y2, lines y1, y2, lines log of y1, log of y2. That's all. y1, y2, log of 1, log of y2. There you go. So this is the first problem. It's very simple. Then comes the next problem. We don't need to simulate anymore. Okay, coming to the next problem. This is just graphical representation. Estimating the exponential model by maximum likelihood, where simulate the model beta naught exponential of beta 1 xt plus ut for example of t is equal to 50, with the exogenous variable, the disturbance term, and the parameters are defined as exercise 1. So the information is given. We need to use the Newton-Raphson algorithm to estimate parameters and concentrate out sigma square, choosing a starting value of beta naught is equal to 0.1, beta 1 equal to 0.1. Compute standard errors of beta naught and beta 1 based on Hessian. Estimate the parameter model without concentrating the log likelihood function. So first concentrate out the log likelihood function, sigma square from the log likelihood function. Then with the sigma squared inside the log likelihood function, we need to estimate them for comparative purposes, nothing else. This is what was discussed in this part. You see, this is the log likelihood function. Okay, let's get into the main thing, then we will basically go through one by slowly. Analyze exponential. So we need to have a look into analyze exponential. Alright, exponential. Is there any local function? Indeed there will be local function, because two things: we need to simulate data, and then we need to define the log likelihood functions. So first, function yx, simulate data for t, random stream, set global stream, blah blah blah. These information is given in problem 1. Then residual is updated, mu sigma into random number t1 r norm. Exogenous variable is 1 to t transposed, and this is the only equation, so this has been updated. In the beginning, the simulate data package is introduced, and simulate data function of t, we need to, the system will give us a simulated data for y and x. So how do you ensure that? Return least y equals y, x equals x. This will give me simulated data for y and x. Then log likelihood function. First, beta yx function, beta yx. This is the function mean of this, and return log likelihood function. Then concentrated at each observation. Now when we are talking about concentrated, we do not need sigma. So without that, what do we have? Concentrating out sigma square, we have function log lt beta yx. Okay, error e is equal to y minus beta 1 exponential of beta 2x. Very simple. Beta 1 exponential of beta 2x. Fine. This is e, and standard error is sigma square is, now we are not using the given sigma square, we are estimating our own sigma square, which is e transpose. This is u, this is basically u residual. E transpose, because they are both matrices, so percentage sums come in, divided by the length of e or t. U transpose divided by length of e, and log likelihood function is simply 0.5 log twice pi square twice pi minus 0.5 log sigma square minus 0.5 u square divided by 2 sigma square. Okay, you're confused, give me 1 second. See, 1 by root over twice pi sigma square minus ut squared divided by 2 sigma square. This is the log likelihood function. Simple as it is. Return log likelihood function, then the unconcentrated log likelihood function. Concentrated, and where is the unconcentrated one? No, unconcentrated is just introduce this t. See, sigma square is, do not concentrate out the residual variance. Without concentrating out the residual variance, we have what? We have third parameter, beta 1, beta 2, and beta 3, right? Beta 1, beta 2. Basically, the third parameter is sigma square, beta 1, beta 2. Sigma square is beta 3, that are estimated with maximum likelihood estimation. We're not defining it. So, because we always need this portion, we always need residual, so we cannot just simply concentrate our residual. We're defining the residual here, we're not defining, we're letting the system estimate residual is unconcentrated. So those are the functions. Now let's simply go to the exponential function, exponential model. Very simple. Exponential function, t equals make new random false. Okay, this is either this is instead of flag, right? Either simulate data or use the given data. Instead of simple flag or not flag thing in R is quite big. Make new random, make it false. If make new random is true, then simulate data. X is from the simulation results, X will go to X, Y will go to else. Simulate result will only take tables that is produced where Y is the first column, X is the second column. We'll always simulate data if necessary. Okay, this is good to give some option to the user. Flag 1 or flag 0. Alternatively, this is estimate the model. So start C, point 1, these are given to us. Theta if any now, theta neg log, theta yx start. Optimization, this is par, which is the start, which will be replaced. Neg log y equals y, x equals x method, Newton-Raphson. Theta is replace par. Hessian is numeric Hessian neg log theta transpose yx, neg log theta yx, very simple. Hessian theta transpose, because probably the theta is in rows, or will automatically understand. The variance covariance matrix is simply inverse 1 by t, inverse of theta. So we have concatenate and display. n starts with n, ends with n. Parameter estimates is theta. Negative Bayesian matrix, covariance matrix. That's all we needed to actually estimate. Very simple. Okay, so this is exponential model using Newton-Raphson. So concentrating out variance and non-concentrating. Now estimating the model by Gauss-Newton. It will be a bit challenging because Gauss-Newton has a few steps, as we are already aware of that with OLS. Simulate the model for the sample size of t equals 50 with the exogenous variable and the disturbance terms are as defined in exercise 1. Use the Gauss-Newton algorithm to estimate theta equals beta naught, beta 1 and sigma square. Choose a starting value for beta naught, which is 0.1. Beta naught which is 0.1 and beta 1 which is 0.1. Compute standard errors for beta naught and beta 1. We need to define the default tolerance here because remember, beta naught and beta 1 estimation with Gauss-Newton will continue up until is less than the default tolerance. Compute the standard errors of beta naught, beta 1 and compare these estimates with the estimates we received from Hessian in exercise 2. Okay, great, not bad. Let's just remove this Gauss-Newton. Exponential. Let's see. Obviously we'll have, we don't have any functions. Okay, fine. First of all, we'll start with simulation. We update y and x as it is. Then we will start with the Gauss-Newton algorithm, and there comes the interesting part. First, we have the starting values with us. Then a default criteria. Okay, because beta naught, beta 1 will continue up until it's less than the default criteria, where it will converge, as we know. And we want to define maximum number of iterations, which is 20. This is new. Let's see how R is handling it. Starting values, default convergence criteria, maximum iteration, nothing. Okay, there is no. So for I equals 1 to 20, for up until maximum number of iteration, we have the residual. Then we have Z1, exponential of beta 2x. Let's see if we can recall what was Z1 and what was Z2. Right, so we just need to look back for Z1 and Z2. So we are in the nonlinear regression functions exponential model. There is Z1, exponential of beta 1 xt, Z2, beta naught, exponential of beta 1 xt multiplied to xt. So this is what it is. Beta 2 this is first parameter. Because beta 1, beta 2, this will be estimated with Gauss-Newton. Beta 2 xt, beta 1 x into x. Let's see. Exponential of beta 1 xt, beta naught, exponential of beta 1 xt. B1 is beta naught, exponential of beta 1 xt into x. Z is equal to Z1, Z2. So exponential of beta 2x, Z2, beta 1, third bracket, elements going to, array is going to third bracket. No element by element multiplication is there. It automatically understands whether it's element by element or not. No. And then column bind Z1 and Z2. So iteration, number to string, number of iterations is going. We change is Z by E, which is actually delta, which is actually calculating the change Z when evaluating U. What is this? Very simple. This is this part. Evaluate U, Z1t and Z2t as starting values of beta. Regress U on Z1t and Z2t to obtain the delta hat beta naught and delta hat beta 1. B change is that we are regressing U on Z1 and Z2 to obtain the change delta 1 and delta 2. If delta 1 and delta 2 that we are analyzing, if those squared is less than critical value, then that's all we need to do. Otherwise we'll have to continue. So this is because here update the parameters to estimate iteration k equals 1. See, this is the change and this is B, right? Elements in B, elements in B change. This will continue up until convergence, right? This we want it to continue up until convergence is achieved. So if B change transpose and B change is less than critical value, multiply to B change, which was this needs to be multiplied. There's a little error, it's not comma, it's multiplied. So less than critical value, break, otherwise update new parameter. So if transpose of B change multiplied to B change is less than critical value, break, third bracket starts, break. Wow, this is new. Else second bracket starts, second bracket ends, else second bracket is a new line, it's one line, it's the second line, else you update. If when I equals maximum number of iteration, this means equals if E is within first bracket, the whole thing is within first bracket after if. Is not in case of MATLAB. Failed to convert up to iteration number. This maximum number of iteration retrieved starts with an N, ends with an N, equals maximum. That's all. So for this, you see here with R, the good thing is, well, you just need to concentrate on the number of second brackets. You don't need to concentrate on a lot of ends, you see. So here is one command, here is one command ending. It's an error because there must be a bracket here, that's all. So ending here. On the other hand, this if is ending here, whether this if is ending here, right? Okay, there you go. And then we have u square by t, sigma square equals u square v divided by t. We already know that. If you still want to check, sigma square equals u square by t, information matrix, omega is equal to sigma square inverse of z transpose, right? Sigma square z transpose sigma square t z transpose, information matrix, and we are concerned with inverse of the information matrix, which is covariance matrix. Omega gives us what? Omega gives us mean information matrix inverse sigma square Oh, we are talking about covariance. Yeah. Inverse sigma square. So basically it should be sigma square divided by ZZ transpose. Sigma square divided by ZZ transpose should be the covariance matrix. That's all. So S2 is column bind T transpose multiplied to E, transpose of E multiplied to E divided by T. Omega is simply that. Okay, this is residual variance in column. That's what I want. That's why. So parameter estimates, standard errors, and t-statistics. So parameter estimates starts with an N, ends with an N, print, column bind, B, parameter estimates, then residual, standard errors, square root of diagonal of omega, diagonal elements is square rooted, t-statistics is B by standard errors, estimated asymptotic covariance matrix is omega. So basically this is how we are doing Gauss-Newton. It's quite simple and a bit different, but I think it's more efficient and consistent compared to Newton-Raphson because we are allowing a convergence to happen. Okay, so this was the third problem. Let's have a look at the fourth problem, nonlinear consumption function. So we have constant contest, two problems. The exercise is based on United States quarterly data for real consumption expenditure and real disposable personal income for the period March 1960 to December 2009, downloaded from the Federal Reserve Bank of St. Louis. Consider the log likelihood function. Consider the log likelihood, consider the nonlinear consumption function C is equal to beta naught plus beta 1 YTB. Okay, this seems quite big. Consider the nonlinear consumption function C equals beta naught, beta 1 YT, beta 2 plus UT. Estimate the linear consumption function by setting beta 2 equals 1. Estimate the unrestricted nonlinear consumption function using Gauss-Newton algorithm. Choose the linear parameter estimates computed in part A for beta naught and beta 1 and beta 2 equals 1 as the starting values. Test the hypothesis using LR world and LM test. Okay. To completely do the fourth problem, we need to go through some theories one more time. Well, we can come back to the theories later, I guess, because no, we'll just go through the theories first. So asymptotic distribution, maximum likelihood estimators are asymptotically normally distributed in the context of nonlinear regression model. This means theta hat is normally distributed with theta naught is the mean and the variance is inverse, well, is the covariance matrix, or omega, which is the inverse of the information matrix, in which theta naught is equal to beta naught and sigma square, unknown parameters, is the true parameter vector, and information matrix is the information matrix. I theta naught is the information matrix evaluated at theta naught. The fact that I theta naught is a block diagonal in this class of models considered here means that asymptotic distribution of beta hat can be considered separately from sigma hat square without any loss of information. Now, information matrix is equals expected ZT transpose divided by T sigma square, as we already have seen before. So that asymptotic distribution is beta hat is equal to mean is beta naught, with the distribution asymptotic distribution with mean is beta naught and variance is sigma square, information matrix inverse, which is just opposite of this without the t, sigma square divided by expected value of zt z2 transpose. In practice, sigma naught square is unknown and replaced by sigma hat square, which is the nonlinear function differences of dependent and independent variable divided by t whole square. The standard error is computed when we simply divide sigma hat square with zt z2 transpose. The asymptotic distribution of sigma hat square is thus 0 and mean is sigma square naught and variance is 2 sigma naught 4 divided by t. So we talked about two asymptotic distributions. First one is the asymptotic distribution of information matrix, then the asymptotic distribution of sigma square. So asymptotic distribution of information matrix and the asymptotic distribution of sigma square. Now important part, going back to one most important part, is testing, which you will need for solving number 4, Euler world and LM test. Testing a nonlinear consumption function, and null is beta 2 equals 1, alternative is beta 2 not equals 1 for t equals 200. So the log likelihood function of theta naught is half log tau square minus half log sigma square minus 1 by t, ct minus beta naught minus beta 1 yt divided by 2 sigma square whole square. Log likelihood function of theta 1. So theta naught is z1 and theta 1 is z2. As we remember, z1 doesn't have yt beta 2. It only had beta 1 and beta 2 on the other hand, z2 on the other hand had beta 2. So to be very precise, yeah, z1t was exponential of beta 1 xt, z2t was beta naught exponential of beta 1 xt multiplied to xt. So basically that's why beta 1 yt beta 2 is included, exponential beta 2 is included in theta 1. Given concentrated log likelihood for restricted theta naught is restricted here, and you remember in concentrated case we just do u ut transpose divided by sigma to u square divided by 2t to estimate the variance sigma square. So u square by t. Restricted theta naught is this. You see beta 2 is not here in theta naught. In theta 1 beta 2 is included. So beta 2, beta naught, beta 1, beta 2, sigma square is 1, variance is just 1. In restricted and unrestricted, sigma square is estimated. The p-value is 0.000, means linearity restriction is rejected to perform wall test. R001 and q equals 1. Linearity restriction is rejected when we perform wall test. So beta naught, beta 1, beta 2. So restricting, we are testing against beta 2 if it is 0 or not. And q equals 1 because there is just one element where we are putting restriction. Or basically q equals 1 means either there equals 1 or there not equals 1, null and alternative values. Computed Hessian wall test is t or theta 1 minus q transpose r inverse Hessian multiplied to theta 1 hat r transpose theta 1 minus q. P value is 0.00. So transpose, non-transpose and r transpose, this is the decomposition. Theta 1 multiplied to Hessian. meaning linearity restriction is rejected at conventional significance level. T gradient 1 by OPG, gradient transpose gradient. So, and this is the decomposition. P value is 0.000. Restriction is rejected. Restriction is rejected. LM over test and LR test. So example 6.9, constant marginal propensity to consume. This is an example that we will deal with later. Propensity to consume. In the example of CT is equal to, now this is number 4 problem which we are dealing with now. Beta naught plus beta 1 YTB plus UT, nonlinear consumption function with unknown parameters beta 1 naught, beta 1, beta 2 has a marginal propensity to consume given by this, which is DDYT for CT, which is beta 1, beta 2, YT beta 2 minus 1. The value of which changes over time as it is a function of income. This is a function of income YT, so the value will change. Testing the restriction that marginal propensity to consume is constant and does not depend only on YT involves testing the hypothesis now beta 2 equals 1, alternative beta 2 not equals 1. Define Q equals 0 and the marginal propensity to consumption function beta naught beta 2 YT beta 2 minus 1 minus beta 1. Covariance of C B minus Q equals d theta transpose negative inverse Hessian. D theta is the marginal propensity to consume 0, beta 2 YT beta 2 minus 1, beta 1 YT beta 2 minus 1 plus beta 2 log of YT. Beta 1 YT beta 2 minus 1, beta 2 YT beta 2 minus 1, nothing changes. Beta 1 YT beta 2 minus 1 multiplied to 1 plus beta 2 log YT. Okay, fine. So general form of work test is T C theta minus Q, C theta minus Q transpose d theta 1 by inverse Hessian d theta transpose. It's a chi-square with a chi-square distribution. LM test has a convenient form for nonlinear regression models because of the assumption of normality. To demonstrate, consider LM statistics based on information matrix, gradient, information matrix, inverse, gradient, chi-square distribution. M here is the number of restrictions. Using GT in gradient matrix we have ZTUT divided by sigma square, and in information matrix we have ZT transpose divided by sigma square T. We are getting these from before as we can recall. So LM is T ZTUT sigma square T, ZTUT sigma square T transpose, and the regular one, and information matrix is ZT transpose divided by sigma square T. So this T is out, the whole thing is out, so we have 1 by sigma square ZTUT transpose multiplied to ZTUT divided by ZT transpose, or we can write this as 1 by UT transpose becomes U square. So 1 by sigma square is T by U square because sigma square equals summation of U square by T. So replace that, and next remains same. So we have TR square, which is the LM test statistics. R square is the coefficient of determination from the second stage regression, and all quantities under null is YT equals YT minus mu xt theta naught ZT equals DUT by d theta sigma square is equal to YT minus mu xt theta naught square by T. Okay. So Is this the coefficient of determination from second stage regression with all quantities under knowledge? It is yt, zt is dd theta ut, sigma square is yt minus xt theta square by t. So this is something we need to remember. So there's an example we'll discuss very quickly. Nonlinear consumption function. Previously we used var test to test for a constant marginal propensity to consume in a nonlinear consumption function. To perform on LM test of the same restriction, the following steps are required. Write the model in terms of ut. Obviously, step 2, compute the derivatives z1t, which is db naught for ut, which is 1, b naught is 1, ddb1 for ut is yt beta 2, ddb beta 2 for ut is beta 1 yt beta 2 log of yt. Step 3, estimate the restricted model by regressing ct on a constant and yt to generate the restricted estimates of beta naught and beta 1. Evaluate ut equals ct minus beta naught. So we are regressing ct on a constant and yt so that we can get beta naught and beta 1. Ct is being regressed on the constant and yt, so we can get beta naught and beta 1 parameters. Now beta 1 and beta naught and beta 1 parameters are used to estimate this equation ut. Okay, evaluate ut at the restricted estimates. Now evaluate ut at the restricted estimates when z1t is 1, z2t is yt, and z3t is beta yt log of yt. Okay, regress ut again on z1t, z2t, z3t and compute r square. Evaluate equals r square. So there are 6 steps. First, we need to write the model in terms of the residual. Then we need to compute the z's. Okay, then we need to estimate the consumption function model by regressing c on the constant and yt. That will give me beta naught and beta 1 hats, the estimated parameters. I'll put in the beta hat and beta naught estimated parameters, so that I can get the residual ut. So this is the process, regressing yt, and this is the process that we will do. Well, we are gonna do the nonlinear consumption function. Now let's move into discussing the nonlinear consumption function. So first, let's have a look into nonlinear regression model. We have done this problem is NLS conest and NLS contest. Conest and contest. Exponentials are done. Yeah. Conest. First we'll look into conest. Okay. Let's see if we have any. No, we don't have any local functions. So we load the data. All true is list is equal to is all true. RM graphics is off. Load. You're gonna load the data. Then, well, yt is income. Ct is coming from income. Ct is consumption. T is equal to length of yt. So here's data, second column, first column. Estimate the linear model to use as initial starting value. B equals 1. Okay, how am I doing this? Very specifically mentioned, regressing ct on a constant and yt to generate the restricted estimate of beta naught and beta 1. Okay, First, represent the model with CT, then regress CT with a constant and YT. Starting with step 3, once T1 YT divided by CT. Estimate the linear model to use initial starting values. Okay. Regress CT on a constant and YT. So C bind, column bind, repeat 1 for T times, and YT minus 1 coefficient. Then we are doing Gauss Newton algorithm, where alpha is 1, beta is B2, gamma is 1. Alpha, beta 1, beta 2 and gamma is given to us. This is the convergence criteria, when maximum number of iterations we want is not more than 20. Okay. See beta naught, beta 1 and gamma. We're taking gamma as 1, just assuming gamma as 1. Fine. So for up to maximum number of iteration, first we are representing the consumption function with ut, then z1t equals 1 t rows 1 column. Let's have a look very carefully. First, write the model in terms of ut, then z1t 1, z2t yt beta 2, z3t beta 1 yt beta 2 log of yt. z1 once t1, repeating 1 t times for I equals 1 to maximum number of iteration. Zt is equal to yt to the power beta 2, where I'm assuming there's gamma. Okay, so instead of writing beta 2, I'm representing that with gamma, because beta naught is b1, beta 2 is beta, and gamma is 1. So yt to the power gamma, yt to the power gamma. Z3t is beta alpha beta 1 yt beta 2 log. So very simple, 1 yt beta 2, instead of beta 2 I'm saying it gamma, then beta 1 log of yt beta 2, which is yt gamma. So beta log of yt, beta is coming in place of beta 1, so alpha is beta naught, beta 1 is beta, gamma is beta 2, beta into log of yt into yt gamma. That's how it is, very simple. So next we are representing z1t, z2t and z3t. Y, estimate the restricted model by regressing CT on a constant and yt to generate the restricted estimates beta naught, beta 1. So y equals et, x equals z1t, z2t, z3t. B change is x by y. How this is coming? Alpha, beta, gamma. Very simple. Y equals et, x column bind, B change. Now let's look into B change. B change is coming from here. Evaluate ut, fine, residual. Then evaluate ut at the restricted estimates z1t, z2t and z3t, and regress ut on z1t, z2t and z3t. So what I'm doing is I'm evaluating yt and I'm regressing CT. I'm regressing CT, instead of CT is y. I'm regressing CT on a constant. Oh, that has been done before. Basically I'm regressing y equals ut, so I'm regressing ut on z1t, z2t and z3t. This is step 6, regressing ut on z1t, z2t and z3t and computer square. So B change is regressing ut on z1t, z2t and z3t, or linear model. Y regressing ut on z1t, z2t and z3t minus 1 coefficient. So if now I'm doing the convergence criteria, if B change transpose into the change, which is delta transpose into delta, is less than the critical value. From previous example we know that we break, otherwise it will happen as alpha, update new parameters, alpha plus b change 1, beta, beta plus b change 2, gamma, gamma. Very simple. So here ends this, includes if, else if, this is else if. So else if I equals maximum number of iteration display. See, there is an error in the previous example, failed to converge after iteration in terms of bracket, second bracket. So end, see, end, very simple. Then SSR or residual sum of squares is equal to y transpose into y by transpose, and sigma square is SSR by t. Now you can ask, where am I getting these things? We have already discussed this, SSR and yeah. We have already discussed this beforehand. So SSR by t, which is residual sum of squares divided by sum of square residuals divided by t. Information matrix is ZZT, ZZ transpose divided by sigma square. That is something you also know from previous calculations. Yep. Okay. And inverse of information matrix is alpha, beta, gamma, square root of diagonal elements of the information matrix. So as we can see, it is quite not complicated at all, just like before, exactly in the problem as before. We have calculated sum of squared residuals, y transpose y, both are matrices, so multiplied with a percentage sign. Then column bind information matrices. Information matrix is transpose of z multiplied to z, both are matrices, divided by column of sigma square represented in column. Fine. And then inverse of inverse matrix, which is estimated asymptotic covariance matrix, inverse of inverse matrix. And standard error is simply the diagonal elements of square root of inverse matrix, and beta hat are alpha, beta and gamma represented in column. Very simple. So next we move on to discuss the same problem, but we are gonna estimate the test LM, LR and wall test for this problem. Thank you.